So welcome everyone, distinguished guests, colleagues, ladies and gentlemen, tēnā koutou, kia ora koutou katoa. As you've heard, my name is Professor Grant Gilbert, I'm the Vice-Chancellor at Victoria, and it's my great pleasure to welcome you all here for the 14th Annual St. Lee Lecture in Antarctic Studies. I'd like to extend a particularly warm welcome to our guest speaker this evening, Eric Rignot, who is a Professor of Earth System Science within the School of Physical Sciences at the University of California, Irvine, and a Senior Research Scientist at NASA's Jet Propulsion Laboratory. Victoria University's involvement in Antarctic research goes back more than 50 years. Every year since 1957, Victoria staff and students have ventured to the continent to conduct field studies for a variety of different research projects. The University's involvement with this region sits well with our commitment to enhancing sustainability and also to our vision of being a global civic university, that is, a university that contributes to the resolution of some of the world's most pressing challenges as they relate to the global commons. Of particular note in the story of Victoria's Antarctic research was the establishment in 1972 of the Antarctic Research Centre. The Centre has led the way in developing drilling systems to extract geological cores under the seafloor and provided an excellent platform to better investigate climate history and advise the public and government on climate change matters. The Centre is a great example of the calibre of Victoria University's research. It is growing to be recognised as one of the world's leading groups in Antarctic science and a key player in major international research programs. The annual St. Lee Lecture is an important event in the Centre's calendar. It provides a valuable opportunity to hear from an internationally renowned guest speaker and to celebrate the successful collaborative research programs being undertaken by our scientists. Professor Rignot's visit is due to the generosity of Dr. Lee Song-Ti, for whom this lecture series is named. Dr. Lee has an extraordinary record of philanthropy and support for scholarship that spans several decades. Dr. Lee, who received an honorary doctorate of literature from Victoria in 2006, has supported a number of prestigious universities throughout the world, including Oxford, Cambridge and Harvard, providing funding for libraries, fellowships and annual lectures. He has a keen interest in fostering excellence in education and has made generous gifts and donations to universities he regards as centres of excellence. Victoria University is proud to be counted among these. Events such as this annual lecture contribute to achieving the Antarctic Research Centre's mission to better understand Antarctic processes and their influence on the global climate system. The primary research interests of our guest lecturer this evening lie in measuring changes in the polar ice sheets from satellite observations. He leads a very significant research group with members based at both the University of California and at NASA's Jet Propulsion Laboratory. The group's research focuses on understanding the interactions of ice and climate, ice sheet mass balance, ice sheet-ocean interaction in Greenland and Antarctica, and the current and future contributions of ice sheets to sea level change. Professor Rignot's scientific achievements have been recognised through many awards, including NASA Exceptional Scientific Medals, a NASA Outstanding Leadership Medal, and being made a Fellow of the American Geophysical Union. In 2007, he was a member of the Intergovernmental Panel on Climate Change, awarded the Nobel Peace Prize. And if you happen to find yourself north of the King Peninsula in Antarctica, you might be able to spot the Rignot Glacier. The 7-kilometre long glacier was named in his honour, recognising his substantial and important research into understanding Antarctic glacial mechanics. In addition to being a leading scientist, Professor Rignot is highly regarded as a scientific communicator. His research has been covered by major dailies such as the Los Angeles Times and the Washington Post, by the BBC, CNN, National Geographic, Rolling Stone and the New York Times Magazine. It was featured in the Emmy Award-winning 2011 documentary Chasing Ice, and in 2015 Eric was interviewed by HBO's groundbreaking news magazine series Vice, which tackles issues of global importance. In this evening's lecture, Eric will review the current knowledge of ice sheet mass balance and address the questions: Have some of the marine-based sectors already passed a point of no return? And if so, what is the magnitude of sea level rise we are committed to? We will also explore the emission mitigation pathways that can limit the amount of sea level rise by the end of the century and beyond. Ladies and gentlemen, please join me in welcoming Eric to the podium. Thank you.
Can you hear me? Is that all right? All right. Thank you very much for having me here. Thank you for the invitation, Tim. Thank you for inviting me to the Lee lecture. I'm very honored to be here. Sorry it took a little while for us to get our acts together. My background is in satellite and airborne observations with a bit of basic physics and physical oceanography, and the aim to make numerical models better in the long run. I don't get my data from Twitter or Facebook. I get them from real observations. What I hope to achieve in this lecture this afternoon is share with you some of the results we have about probably some of the most vulnerable parts of the Antarctic and Greenland ice sheets. Share with you also how we think it's connected to climate change, to climate warming, and conclude a little bit about some words of whether we should worry about this or not. It's difficult to escape this first slide, but to put things a little bit in context, I apologize for those who know all these details very well, but we have my mouse somewhere on the screen. Oh, this screen, okay. 7 meters of sea level locked up in Greenland, 56 meters in the Antarctic. Snowfall accumulates on these continents very slowly. The precipitation rate on these continents and islands is about 1/10 of the world average, so they are deserts. But because they're so big, they accumulate a lot of mass. Glaciologists used gigatons to quantify mass fluctuations around the ice sheets, 1 billion tons. 1 billion ton is the water consumption of a major city like Los Angeles or San Francisco, depending where you are. It could be Paris or your favorite city. So on the human scale, it's a lot of water. At the scale of these continents, it's a tiny little drop. In Greenland, the accumulation of snowfall, about 600 gigatons, splits between runoff, meltwater that runs to the ocean, and discharge of ice at the boundary with the ocean, typically half as icebergs and half as water, ice melted by the ocean water. In the Antarctic, which is 7 times bigger, we have about 2,200 gigatons of snowfall every year. There's no runoff. Most of the ablation is a little bit of evaporation, sublimation, and wind transport. The ice extends to the ocean, and because the climate is cold enough, it survives in the ocean and forms these floating extensions we call ice shelves, which break up into icebergs and also melt in the ocean. And there too, we find that about half of it is broken as icebergs and half of it melts from below with the ocean waters. This turnover of mass from the ice sheets is about 8 millimeter sea level rise, because 1 millimeter is about 300 gigatons of ice melting into the ocean. And if you do this experiment of mine of multiplying the discharge of all the all the Antarctic glaciers by 6.5, you'll see why 6.5. You could do 6 or 7, it doesn't matter. By 6.5, you would raise sea level by 4 meters per century. Right? 4 meters per century is actually the rate of sea level that took place during meltwater plus 1A about 14,000 years ago, in response to the collapse of the northern ice sheets, but also to some parts of Antarctica that has yet to be identified because there was not enough mass in the northern ice sheet. So it's kind of a pointer of how fast the ice sheets can contribute to sea level, because obviously the point I'm missing here, the obvious point, is that there's nothing else in the Earth system that can create a 4 meter per century sea level rise other than the ice sheets falling apart. Sea level does not rise uniformly. In fact, close to the Antarctic or Greenland, that's a good place to buy beach territory, because the ground will rebound. The sea level will actually fall rather than rise around the ice sheets. And far away from the ice sheets, where people feel that the ice sheets are not relevant to their daily lives, it's actually going to rise faster. New Zealand is in kind of a good spot. You're not going to get the whole bulk of the sea level compared to where we are in California. There's about a 30% difference. So that's important to keep in mind, because we talk a lot about these global numbers, but regionally things can be different from the rebound of the crust, and also because in some places there's some vertical motion of the land. We talk about the 64 meters of sea level locked up in the ice sheets, and half a meter in all the mountain glaciers in the world that are melting away. We don't really need to melt all that to be in trouble. We start getting in trouble, I think, with about 1 meter sea level rise. 1 meter, because I like the metric system. Maybe we can have tried with 3 feet. So it's quite funny, actually. Everywhere I give that slide, I try a different city. It works every time. With 1 meter sea level rise, Wellington International Airport is partially flooded. So we all know that we receive instructions on flight about water landing, but I don't think any of us want to experiment that, unless the pilot is named Sully. Christchurch Airport, even with 20 meters sea level rise, will still be okay. So we can still fly to New Zealand for a while. I'm going to try preparing phone call. This is interesting. We love Windows. Try to explain in this slide, if it ever comes up, what's happening in terms of the climate in the Antarctic. It's reading all the files. So in the Antarctic, as you don't see here, there's a wind regime that moves clockwise around the Antarctic continent, the westerlies, very powerful winds. They blew off my glasses, or the remnant of the westerlies blew off my vision glasses when I was running on the beach the other day. And running clockwise, and the strength of the wind is governed by the temperature difference between the Antarctic and the rest of the world. Right? When the temperature difference is large, you have very strong winds. When it gets smaller, you have weaker winds. And what's happening right now is that that difference in temperature is increasing as a result of greenhouse gases and as a result of the depletion of the ozone in the Antarctic. They both work the same way. They tend to make Antarctica not warm up as fast as the rest of the world. The rest of the world is warming faster than the Antarctic. The Antarctic doesn't have a positive albedo feedback. It's still white. The sea ice surrounding it is still white, very different from the Arctic. And the ozone hole is cooling the Antarctic. So this difference in temperature is increasing. That's increasing the winds, and it's been estimated to have increased the winds about 30% in the 80s. It's a pretty unique event in the past 1,000 years, and you can go back to ice core records and realize that the change in westerlies have always had a big influence on what's happening in the Antarctic continent. So what happens as a result of that, when you strengthen the winds, not only they strengthen, but they also come closer to the pole. So if you remember Coriolis, resume slideshow. I'm having technical problems here. Sorry. This didn't happen yesterday. The surface waters are deflected to the right, to the left of the wind. So they are pushed towards the north, and that explains a little bit the expanse of sea ice in the Antarctic. To compensate for that, the subsurface waters are pushed towards the Antarctic continent. And these are the waters that are actually warm. Yeah, we may have to restart this thing because It's not coming through. And in the polar waters, you're not going to see the westerlies, but they're there, believe me. In the polar waters, it's very different from the mid-latitude, the tropical regions. You have cold waters at the top, cold and fresh. They're cooled by the atmosphere, and fresh because of the melt. And you have warm and salty water at the bottom. They stay there, they're happy because they're salty and denser. And they're typically 400 meters below the surface. The bulk of the warm water is actually more like 700 meters below the surface. And you find it around the Antarctic circumpolar current, the biggest ocean river system you can find on the planet. Right? It carries 10 sverdrup of water flux. And obviously, the places where the Antarctic circumpolar current gets closer to the Antarctic are more likely to receive this warm water. If the warm water reaches the glacier ice, we know that glacier ice can melt extremely fast. Bob Binchler used to say, glaciers hate seawater. Right? And if you're not convinced about that, remember basic physics, right? If you put salt on an icy road, it melts immediately because you get an extra 2 degrees of changes in freezing point of the ice with the salt. It's the same with land ice. When it comes in contact with the seawater, it melts like crazy. So melt rates underneath these ice shelves are measured in tens of meters, even 100 meters per year, whereas at the surface, what's happening is measured at the centimeter level. So not surprisingly, we find that the floating extensions around Antarctica that are melting the fastest, that are thinning, and they're losing mass, they're getting thinner with time, are in the proximity of the Antarctic circumpolar current, right, along the Amundsen Sea, Bellingshausen Sea, and the Western Peninsula here, and then along the Wilkes Land part of East Antarctica. Not so much over here on where you have the Filchner-Ronne and the Ross Ice Shelf, which are far from the Antarctic circumpolar current. In Greenland, it's really too bad we can't see that GIF file. It's something very different that's happening. Because the Arctic is actually warming 2 to 3 times faster than the rest of the globe. Right? There's very strong albedo feedback in the Arctic. The sea ice cover is disappearing. Pretty soon we could have no sea ice left in the summer months. So the ocean is absorbing a lot more heat instead of reflecting it from sea ice. So the temperature differential between the rest of the globe and the Arctic is getting smaller, and the winds is getting less strong. And when it starts doing that, the jet stream, instead of staying very tight around the pole, starts to wobble around, the wobbling of the jet stream. And this is something Jennifer Francis has been putting on the table for a while. And the jury is still out on whether this is the way it works or not. That's why we usually use computer models to explain that rather than real data, because in real data it's a bit of a mess. But you have these large wobbles, right, which are going to send big spill of cold Arctic weather down farther south, like you get that on the east coast of the US, right? Whereas in California, I'm riding without a shirt. In the US, they're freezing to death, in the eastern coast. And you can have other areas, and that happens a lot in Greenland, where you have warm masses of air and warm ocean that goes farther north than usual. Right? And the other interesting thing about this wobbling is that the wobble will start moving at lower latitude. Instead of contracting, it expands. And these wobbles tend to remain fixed in space for a long time. So you can have these cold air masses or warm air masses that don't used to be there that get stuck for weeks at end. So that sort of wobbling of the jet stream is, in my opinion, what explains what happens a little bit in Greenland, and that was not really projected. The fact that we have a little bit more warm Atlantic water making its way up on the Gulf Stream, deflected by Iceland, around the tip of Greenland. Most of it returns to the Labrador Sea, but some of it makes its way in Baffin Bay, and some of it also, as is not shown very clearly in that graph, makes its way all around Greenland and returns over here through the Nares Strait, goes all around Greenland, and affects the glacier, of course, in a very significant way, because they hate warm seawater. Another aspect that's really important to understand, to figure out what's happening to the ice sheets, was developed in the late 50s, early 60s by the people on this chart, and there may be others. I apologize if I forgot some. But it was shown very early on that if you grow an ice sheet on an otherwise flat bed, you're going to depress the bed in the middle. So it's going to have a back slope, a reverse slope, a retrograde slope. And there's only two stable positions for an ice sheet in that configuration. Either it reaches the edge of the continental shelf, or if it starts retreating down that path, the next stable state is a floating ice sheet. It cannot stay stable like that. It will go through an irreversible retreat. If the bed is sloping up, because there's a bump in the bed, it will retreat more slowly. Right? It will counteract that factor. The ice sheet folks have been debating this a lot. The people studying mountain glacier, they go like, we know that. That's called the tidewater glacier cycle. Right? When the glacier retreats down the deeper bed, it goes down in an acclimatic fashion. In addition to that, these folks devised, with very little data that they had at the time, in the case of a confined ice shelf, means that the glacier starts floating in the ocean, and that floating extension shears along the bay walls and then gets anchored on some small islands. That creates some sort of a cork in the system, a plug, that prevents the glaciers from flowing as fast. And they devised that if you were to remove these ice shelves from climate warming, the glaciers would speed up a lot. That sort of theory was disputed a lot in the interim because we didn't have a marine ice sheet collapsing in our backyard to check it out. Their models were also very simple. But as you find often in science, in the first theories of that sort, the models were simpler, very simple, but the people who came with it were pretty smart. Right? We found out, unless we talked to the mountain glacier people, we found out that they were right. When we look at the collapse of ice shelves in the Antarctic Peninsula, in 1995, Larsen A collapsed. In 2002, Larsen B collapsed. And the glaciers upstream of this ice shelf sped up by a factor 3 to 8. So the collapse in 2002, that was 15 years ago, the glaciers are still flowing at that fast speed today. So the cork was removed. The glaciers started spilling ice into the ocean, raising sea level, exactly like these theories from the 60s projected. And in terms of sea level, what happens in the Antarctic Peninsula is a minuscule drop of water. We're talking about centimeters of potential sea level rise. But it shows that if this were to happen further south, we would unleash meters of sea level rise. There are different ways to look at the state of mass balance of ice sheets. The kind of most powerful way to look at this these days is the GRACE mission, the gravity mission. It measures the change in gravity since 2002, gravity field over the Earth. So it actually weighs the ice sheet. Right? The other ways to measure the ice sheet mass balance is to measure the height with time, or as I do, compare the snowfall with what comes out as iceberg and meltwater. GRACE measures directly the weight. It has a limited resolution. It doesn't see details at the glacier level, so that's why you get blobs of mass loss in an area rather than an individual glacier, but it's a pretty accurate way to do this. We also spent some time comparing the different techniques, and they broadly agree in most sectors, apart from a few places. And what we find here, you see this is a plot of the mass with time for the mass of ice. It's just a relative measurement. There's no absolute reference in that. You look at the change in mass. For Greenland, the Antarctic, and all the mountain glaciers in the world. GRACE is the only technique actually that can afford to do that because it's awfully complicated to monitor all these glaciers. We don't even know how many there are. You see that this curve is not a straight line, it has curvature, which means that the mass loss is not constant. It's increasing with time. So right now, Greenland, during that time period, 2002-2016, it's ahead of the game. It's losing more mass. The mountain glaciers are not far behind. And Antarctica is catching up. because it has a little bit more curvature. We did not expect the ice sheets to be sort of competing with the mountain glaciers already now. It was expected to happen much later. If at acceleration I use 44 gigatons per year, because this is what we get when we extend the record another 10 years, and also when we go even back to the 80s, you get a sea level change from melting ice of 78 centimeters per century. So you add thermal expansion to that, that's about 20, 30 centimeters. So we're basically on pace for 1 meter per century sea level rise today. Now I'm going to spend the rest of this talk focusing on what I call sea level commitments. Places in the Antarctic and in Greenland where changes are taking place and they hold a lot of sea level potential. We're not so worried about the land terminating glaciers. The land terminating glaciers are not in contact with the ocean waters. They usually flow at the front at their rate of melt. Right? They don't flow very fast, they actually slow down when they come to the front. We don't expect land terminating glaciers to triple their speed. The glaciers that are going to triple or multiply their speed by factor 10 are the ones ending in the ocean. And the ones that are going to contribute the most are those who have a bed below sea level, so that even when we retreat, they still have their feet in warm water. So and this is, by the way, a map from the CRIOSAT 2 mission. All the areas in red show places where the ice sheet is thinning. Don't know the rate here, but it's several meters per year. And this is the same thing for the Antarctic. Right? You see, it's melting all around Greenland, even in the far north. But the far north, remember, is also warming much faster than the south. And in the Antarctic, we see mostly changes around the peninsula, the Amundsen Sea sector, and a little bit of things going on in East Antarctica. So we have 3 big floodgates in Greenland. The Jakobshavn Isberg over here, which holds a 0.6 meter sea level rise. The Petermann Humboldt over here, 0.6 meter sea level rise. And the northeast ice stream with Njogafjordsfjorden and Zachary Istrom with 1.1 meter sea level rise. So I'm going to talk a little bit about that. And I'm going to talk about 2 big guns of the Antarctic, the Amundsen Sea sector with its 1.2 meter sea level rise in West Antarctica. But this is also a part that could unlock the rest of West Antarctica, which has a total of 3 meters sea level rise. And the Totem Glacier, a single glacier in East Antarctica that holds 4 meters of sea level rise, all on its own. Okay? No need to get help from his friends. Jakobshavn Isberg lost its floating ice shelf in 2002. If you look at the position of the front here with time, it basically retreated more in the last 10 years than in the previous 50. It's retreating down a deep trough. This is a recent mapping of that trough. The glacier is retreating down this slope here, so it's a retrograde slope. There's some little bumps, but it's mostly retrograde. It's going to drip down to 1,600 meters below sea level. It's not there yet. It's retreating at 0.6 kilometers per year since about 2002, pretty steadily. It's going to keep doing that for 20, 30 kilometers, so it's going to be busy doing that for the next few decades. It's sped up as a result of the loss of the ice shelf by a factor 3. It's experimenting now very strong seasonal fluctuations which did not exist in the past. It went up to 18 kilometers per year speed in 2012. In the summer of 2012, that's a whopping 50 meters per day. Right? At those speeds, you can almost see the ice moving with your naked eye. Right? It's retreating down a deep canyon. It's pretty much like the Grand Canyon, connected all the way to the center of Greenland through submarine channels. The next floodgate I wanted to talk about is the Northeast Ice Stream, a giant feature here that goes all the way to the summit of Greenland. That's the closest analog in Greenland to Antarctic glaciers, but this is indeed a place where climate is cold and precipitation is very low comparable to the Antarctic. There are two glaciers, the 79 North, Njögafjordsfjorden, and Zachary Ström. And Zachary Ström lost its ice shelf starting in 2004, but it took a little while before the whole ice shelf collapsed. It took about 8 years. It's sped up by 0.5 and 50%. It's retreating right now in a bed that's a little bit retrograde, 600 meters below sea level, before it hits a little jump farther inland. And Zachary controls half a meter of sea level rise, 79 North controls another half. There are some pathways for the ocean to follow the glaciers. Some of these corridors may be a little bit narrow. There may be places where it rises a little bit above sea level. We don't have enough details to be sure, but you see that there's some connection with the inland basin that's below sea level. 79 North is also melting, and we know it's melting from below. It's melting because the ocean has gotten warmer in these areas. It's retreating up a prograde bed much slower, 100 meters per year. Right? The prograde, 100 meters per year, retrograde, 500 meters per year, factor 5. I have a little animation here that goes back to the 70s, which shows the ice shelf in front of Zachary Ström and how it retreated over that time to be completely gone by 2012. So the glacier used to have a floating extension. Now it's calving along an ice wall. The third floodgate is Petermann Glacier. I put a little movie here, that's where we were there in 2002. The guy was bending to the side to avoid the wing of the airplane is Connie Stephan. He survived. So that ice shelf was fairly stable until recently. 2002, it was pretty happy. I always told Connie, we're going to come back when something happens here. But then it lost 30% of the floating ice around 2010. The glacier had been stable since the first days. Humans stepped foot on that glacier, Lance Koch in 1901. It had a very stable ice speed until recently where it's starting to pick up speed. In some parts of the ice shelf we don't see any thinning. In some other parts we see a little bit of mass loss. We have to figure this out. So that floodgate is not quite open yet, but the ice shelf is not doing very well. And if you saw the talk by Jeremy Mugino this morning, he showed you that all the other ice shelves in the area are kind of falling apart or are already gone. There's some nice channels there for the ocean water to follow through the glacier retreat. There's a very deep canyon here all the way for Petermann, and another one for Humboldt Glacier. Retreat, pretty small there for this third floodgate. Now we're going to switch to the Antarctic, right, with these two sectors, the Amundsen Sea and the Totten Glacier. So in the Antarctic, we have 3 meters of sea level rise potential from the marine-based part of the ice sheet. In the East Antarctic, I have 19 meters. There was always, for historical reasons, a lot of focus on the West Antarctic ice sheet as being more vulnerable. It lays lower, warmer climate. It's all marine-based, but we have a big marine-based sector in East Antarctica as well. Right? In terms of the mass loss, I showed these results the other day. These are mass loss in gigatons for that time period, 79 to 2003, 2003 to 2015. You don't have to look at the details of the numbers. Two things are striking from these results. The biggest change in mass loss, the biggest increase, took place over the Amundsen Sea sector, the Pine Island sector. The mass loss quadrupled from 30 to 100 gigatons. And in Wilkes Land, it went from about -3 to -55. And that's not just Totten. There's a whole bunch of glaciers that are changing there slowly. We have some changes in the peninsula as well and other sectors. So in the Amundsen Sea, which was, this sector was pointed out by Terry Hughes as the weak underbelly of the West Antarctic ice sheet. When I first heard about that, I went to the dictionary and said, what does it mean, weak underbelly? Is that a dirty word? Because Terry is a character, as you know. He always makes dirty jokes. I thought there was another one. But he was not joking at the time, except nobody believed him because there was no observation to support his claim that maybe this part of West Antarctica was actually already falling apart. These glaciers all increased their ice discharge pretty remarkably in unison. Between 2002 and 2009, things jumped up. This was also a period where the ocean water in front of these glaciers were a little bit warmer than average. And in 2012, 2013, we saw a return of colder conditions, and some of the retreats slowed down. Models tend to suggest that ocean temperature is, of course, a big modulation on the melt rate, and the melt rate has a big impact on the flow speed of these glaciers. It's kind of remarkable that these 3 or 4 glaciers did that thing all at the same time. Right? Knowing that geometry is important, that clearly says they respond to a common forcing rather than their own geometry. The grounding line on Pine Island Glacier is moving back at 1 kilometer per year. Right? So you remember Jakobshavn? Half a kilometer. And that's an example of marine ice sheet instability. Jakobshavn, however, is retreating down a deep trough. It's shearing along the side. It's really hard for the ice to fall apart because it's constrained by the walls of that trough. Things are much broader in the Amazon Sea. Thwaites Glacier is 120 kilometers wide. I'm sorry, but we can't picture that in our mind. The first time I flew over Pine Island Glacier, I knew how big it was. It took 10 minutes on an airplane to fly across it. I couldn't believe how wide this thing was. If you stand on it, you have no idea you're on the glacier, by the way. Thwaites is retreating at about 1 kilometer per year too, so twice as fast as Jakobshavn. And the Smith Glacier is retreating at 2 kilometers per year. That's the fastest rate of retreat we've measured on the face of the Earth for these big glaciers in West Antarctica. So I show you some details of the bathymetry, right? Because that's new and that's fun, at least to me. This is the Smith Glacier over here, and the Kohler Glacier down there, the Dodson Ice Shelf, the Crossan Ice Shelf. The ice shelf is still there, they're doing fine. And the warm water follows these channels. This glacier here drops down into a bed that's 1,600 meters below sea level. It's a very, very nice retrograde bed, 2 kilometers per year retreat rate of the grounded ice, and the ice shelf is still there. Kohler Glacier, on the other hand, is climbing up on a prograde bed, and we see the grounding line moving up and down all the time. It's taking a little time for that glacier to move up the hill. So, I put a number here that I did not explain. That glacier can keep retreating for another 88 kilometers before it's going to start not running out of the water, it's going to still be in contact, but coming into a bed that starts sloping up. So it can keep maybe retreating at that rate for another 44 years and have a major contribution to sea level. Pine Island has a little bit more of a complex way for the warm water to make its way through. You see the grounding line is over here. It used to be there anchored on these points in 1996 when I first laid my eyes on this glacier. And now it's going into a deeper bed, retrograde bed. There's nothing, there's no bump upstream to stop the retreat. That's why when we had enough confidence in these results, we said, we don't see a point of return for these glaciers. We're going to keep sliding back, followed by the ocean, into a deeper bed. It can go on like this for 200 kilometers. If it does at the 1 kilometer per year rate, which is probably a lower end for the retreat of this glacier, it would do that in 100, 200 years. But we don't really know at what rate they're going to retreat down that path. And then the Thwaites Glacier, which is going to be the focus of a major effort between NSF and NERC in years to come. This is the fast flow core, and Thwaites has also on this side a portion of the glacier that is buttressed by an ice shelf with an ice rise here, which is actually part of a chain of mountain buried under the sea, right? So it's a pretty strong piece of land here that anchors that glacier. But we see the pathways, natural pathways for the subsurface warm water, how it intrudes there and there. And this is indeed where the glacier is retreating the fastest. You see In red here, the position of the grounding line in 2016. This is where it was in 1996, and it's retreating a little bit faster than 1 kilometer per year here and here, following these channels. Right? And if you go along these channels, it just gets deeper and deeper inland. These little bumps are not going to do very much. There's no big bumps along the way that are going to stop the retreat of Thwaites Glacier. Now we're moving on to Totten, for which we had the first indication of something was going on with altimetry. There was some results from Andy Shepard. And I vividly remember he presented that at a meeting on West Antarctica. And the leader of that meeting decided, this is not West Antarctica, you are a poster. I'm like, sorry. There was a lot of focus on West Antarctica at the time. But we had to wait kind of a long time to figure out what's happening on Totten. It's extremely difficult actually to figure out the mass balance of this glacier. I had a PhD student work 6 years of her life to figure this out. And this is what's plotted here. It's losing mass. It lost less mass, strangely, when the reconstruction of the ocean temperature around Totten was a little bit colder. And then it's got warmer, it started picking up again. And last year, Steve Rantoul and his team from Australia got the first measurements ever in front of Totten Glacier and found that trough right in the middle of the face where warm water, it's warm in Antarctic standard, all right? Don't take your bathing suit in there, it's 0 degree. But 0 degree for ice sheets is really bad, right? The melting point is -2, and at this depth, 0 degree is plenty of heat to melt the ice. Good news, though, is that we map a lot of the bed upstream, and it's prograde. It's a prograde bed. It is sensitive to the ocean. It's retreating at 200 meters per year, but it's going to have to overcome some hills before it hits that deep Aurora Basin here in West Antarctica, which holds the 3.8 meters sea level rise. It has to go another 50 kilometers of rough terrain before hell breaks loose, as we would say. But wait a minute, there's another guy here named Denman in front of Shackleton Ice Shelf. We have about 1 ice thickness measurement there across that glacier. Not much study of Shackleton Ice Shelf. I'm sorry for Sir Shackleton, we're going to fix that. The ice shelf is thinning, the glacier is thinning very slowly. When we look at its state of mass balance, it's very close to mass balance. But it's sitting right now on the edge of a sort of a cliff that gets 2,500 meters below sea level, and that continues for about 50 kilometers. So we're going to keep a close eye on Denman Glacier in the years to come. Now, these are the news from the front of the observations, but we had a lot of interesting news from the paleoclimate record. And the two are slowly converging. We used to be communities, we didn't talk to each other, and now we talk to each other. What did you find out? All right. We are on pace for 1 meter per century sea level rise from the ice sheets and glaciers and thermal expansion. But the paleoclimate record suggests that if we get half a degree warmer, like during the Eemian, or maybe not even half a degree warmer, maybe we're already there, sea level is going to be 6 to 9 meters higher. So that means a big chunk of Greenland will have to go, a big chunk of West Antarctica, and we need also something for East Antarctica. To get to 9 meters, you have to involve East Antarctica. So that means if we warm up the climate 1.5 to 2 degrees above pre-industrial, the paleoclimate record says we're committing ourselves to 6 to 9 meters sea level rise. And a lot of numbers that have come since these first studies all converge to similar things. So how is it going to look like? Well, you know, in the 50s, they figured it all out. They knew about climate change. They even made movies about ice sheet collapse. Right? And I hope it's going to show because I had some problems with my GIF file. Ah, damn. Okay. All right. It was a movie made in the 50s. Earth being hit by an asteroid and you see the ice sheet collapse. Well, you will not see it, sorry. Some of the challenges to come ahead in projecting the ice sheets. Figure out the warm water pathways. So we're spending a lot of time mapping the fjords in Greenland. We're doing the same thing in the Antarctic, but in the Antarctic there's a lot of places we can't map, especially beneath the ice shelves. Radars don't work. Remote sensing doesn't work. Right? You have to use gravity data or you have to use seismic methods. This is a map of the trough in front of the Atlantic Sea. We're going to have to figure out the change in polar winds with climate change and how it's going to affect the heat transport, ocean heat transport. And the ocean models are not capable of doing that today. To do this, we need to run these models at high resolution and using the biggest computers on the planet to get results, simulations over decades. We have to figure out the rates of ice melt by the ocean. We have to figure out at what point these ice shelves are going to collapse. We know they're going to collapse once they start melting from the top, but there could be other processes that make them collapse sooner than that. And once these ice shelves collapse, we have to figure out a little bit how fast they're going to carve into icebergs. So there's some interesting news about that when we look at Jacobshavn Bay, because it lost its ice shelf and now it's carving back. And what Ian Jugan found is that the glacier is only carving once it's thin enough to almost reach hydrostatic equilibrium at the front. So the glacier wants to thin enough so a piece of ice can detach from it. That piece of ice wants to rotate, like we see in that little movie, it wants to rotate. It has to be enough space to rotate away from the ice front. So that provides some sort of a limit speed on the calving speed of Jacobshavn. It has been actually calving at 12 kilometers per year steadily since it started its collapse. So there may be some processes that limit the speed of calving of these glaciers, but we really don't know enough at this point to nail it down. So, some words of conclusion. Am I doing good in time, Jim? All right. Sea level rise by 2100, more than 1 meter, very likely. This is not a futuristic situation. It's on pace now. The irony of this is when we started talking about this 10 years ago, everybody was raising eyebrows. 1 meter sea level rise. Yeah, you're crazy. Right? And now it's common knowledge. I watch these interviews, everybody says, yeah, 1 meter sea level rise per century. Sometimes I even want to say, which publication are you referring to? Twitter. Twitter. Sea level rise commitment, to me, that was probably one of the biggest news in the last decade. We see a lot happening in the ice sheets, but the paleoclimate record coming very strong and clean and saying, if you warm the climate this much, it's 6 to 9 meters. Right? When we talk about projecting the impact of ice sheets on sea level, we have an uncertainty of about factor 10. Right? Here they say 6 to 9 meters. Pretty awesome. But obviously, the Paris Accord are great, right? They came back with 1.5 degrees instead of 2 degrees. That's the right move. Except, as scientists, we all know we're going to go beyond the 1.5 degree. We're probably already there. And it's going to be difficult to limit ourselves below 2 degrees. And we know from the paleo record that's not going to protect us from sea level. We are committing ourselves to a 6 to 9 meter sea level rise if we stay in that climate. We don't know how long it's going to take, but we are committing the system to do this. The timescale of these shifts, they're not measured in thousands of years. They're measured in centuries, maybe 1 or 2 centuries, maybe 1. It's not a political timescale, right? But it's a human timescale. You can live 100 years. Right? Some of us will try to do it. The MLCC sector, I'm still absolutely convinced that the retreat in that sector is irreversible. We don't know exactly at what speed it will process. If the ocean doesn't warm up too much, it might go a little bit slow. If it warms up a lot, if there's a lot of heat coming into these cavities, it might not. I've seen recent model results that suggest that once the ice is retreating and forming small cavities, it's actually difficult for the warm water to make its way all the way there. That's a negative feedback that's going to slow down the retreat. But that's 1 meter sea level rise we're coming into, and that part of West Antarctica is going to eat alive the rest of West Antarctica from behind. Right? The other sectors, like plugged with big ice shelves, are going to be hit by behind from all this ice that's removed from the northern sector of West Antarctica. 2 or 3 marine-based sectors retreating in Greenland. 2 out of 3. Jakobshavn. Actually, part of my position about marine ocean instability evolved from the fact that we had discussion during IPCC where some of us were saying, we don't think we've seen anything in the system suggestive of marine ocean instability. And I was thinking, you've got to be kidding me. All right? I do think that these sectors of Greenland, 2 out of 3, are undergoing a marine ocean instability. We've never seen what it looks like before. It might take a little while for us to recognize it, but it sure looks like it. East Antarctica losing mass at an increasing rate. There's some pretty good barriers over there in East Antarctica, but we did not expect to see that at all along the East Arctic coast. These changes are worrisome. On a different timescale than the weather system or Twitter or Facebook, right? You have to wait a few decades and look back and say, wait a minute. Those changes were pretty fast. I remember looking at the collapse of Zachary Strom ice shelf in 2004, and I thought, okay, we're up for some big speed up and big collapse. It took 8 years for the ice shelf to collapse. And then what? It took 8 years, but in a decade it was gone, right? So that's what worries me. The changes are fast. They are on the human time scale. They're not measured in centuries or millennia. They are occurring during our lifetime. And I'll leave you with this, one of my favorite slides on climate warming. Thank you very much.
And I also have the pleasure and privilege of giving the vote of thanks here tonight. So thank you, Professor Rignot, for the lecture you have just delivered and for your passion and dedication which you bring to the subject. So thank you very much. I'd also like to thank Professor Lee Sung-Ti for his ongoing support of the ST Lee Lecture Series. As you've heard, these annual lectures have become an important event in the university calendar and serve as an inspiration to our students, our staff, and we hope the wider community who have interest in Antarctic science and climate change. I'd also like to take this opportunity to thank Professor Tim Naish and his team and the Antarctic Research Centre, who once again have done a wonderful job in bringing this lecture to us tonight. So thank you, Tim. Tim wrote that bit, I must say. Okay, so climate change is now recognised as the major environmental problem facing the globe, recognised by almost all, with the possible exception of the President of the United States. We've heard here tonight about the magnitude of future sea level rise. New Zealand, an island nation, would look markedly different if several metres of sea level rise were to take place. Our coastline would be significantly different, and many places, if not plainly underwater, would experience serious flooding and coastal inundation. In the face of such a potential tragedy of a global scale, our future, or rather our children's future, depends on international consensus and cooperation, bold policy, determined regulation, and significant investment. And it's professors like Professor Rignot who are taking crucial international leadership roles in understanding and communicating the impacts of our warming world, and who need to have our thanks and support in keeping the issue in the forefront of the minds of our political leaders. Now, all that remains is for me to thank you all for coming here tonight. I hope you found this lecture as interesting and inspiring as I have, and I look forward to seeing you again at our next Victoria event, our public lecture. I think there is a reception outside, thank you very much for coming, and have a safe journey home. So thank you.